So, what can I say? Welcome to Thermodynamics.
I have a quick question.
Yes, sir.
So that little piece of paper on the front says
Oh, yeah.
That's our grading class right now.
Yeah, so if I was knew my Canvas well enough, I would have it all loaded in Canvas, but there's issues between me and their grade book. So that's based on what I have turned in. That's the overall grade. And then if there's things missing, homework or labs, what isn't incorporated in there is the air motor lab, which I'm still grading. And I didn't even have time to log in, who had that turned in or not. But up until that point, that's everything I know about.
Is that with the test?
That's with the test, yeah. So we've been talking this Otto cycle. It doesn't matter if we're talking 2-stroke or 4-stroke engine, but we had isentropic process here that we're modeling, and this is ideal gas world, so it's going to have a formula with K's in the exponent. That's your tip-off that you're talking an isentropic process. And then heat goes in and the temperature rises as the piston is sparked at the top and combustion happens. And if we know how much heat went in, we can predict that temperature using the constant volume C sub P, because remember we talked about enthalpy was Q, the quantity of heat is C sub P delta T. Well, for a constant volume process, it's a C sub V constant, C sub V change in temperature. So we can predict this temperature. There's two things going on. Either they can tell us what the maximum temperature was, and we predict what this one was, and then we can back into how much energy would result in that temperature, which is basically solving for Q, or they can tell us how much heat went in. We can solve for that temperature, but we need that temperature so it can isentropically expand in the power stroke, and then the exhaust is magically the heat sort of leaves. But it all comes down to these processes. So let's see what that amounts to. We had some, where's my button? Started setting up the problem earlier when we were walking through this. Here's, in this problem, they told us we have a compression ratio of 8. Now again, compression ratio is about volume, not about pressure. But by golly, if you have some air and you only give it 1/8 the space that it had, it's going to have higher pressure and higher temperature. Ideal gas law says so. Put in that much energy, compression ratio of 8, came in at 100 kilopascals, which is atmospheric. 17 degrees C, which ideal gas law, we need to be using absolute temperatures and pressures. And for a constant volume process, how much heat it takes to raise a kilogram, some number of degrees is 0.855. That's in, and we're treating this as a constant. Is it really a constant? No, it varies a little bit, but if you're close enough in temperature range, then you can get an average value or treat it as a constant. And that's what we're going to do. So again, table, if we can fill out this table, all we really care about is that enthalpy value. Enthalpy tells all the energy due to heat and the work, the pressure times volume. So some of the formulas. In this case, if I can chase the temperature around the cycle, the difference in temperature is going to give me changes in H. This is all I really care about. So in this case, changing H, CCP, delta T. So for ideal gas cycles, chase the temperatures around, and you can use those to get your values. So here's the case. Compression ratio is V1 to V2. Ratio of temperatures to volumes for isentropic process is T2 is going to be T1 times compression ratio to the K minus 1 exponent, which is the K is our ratio specific heats. So let's see what we can do about that. I want to find that temperature 2. So temperature 1, 17 degrees C, well that's nice, but this is ideal gas law. So we have to use 17 degrees plus 273 to get us 290 Kelvin. My R value is 8 to 1 compression. K is, these are what we call air standard cycles, as if air is going around, so K is basically always going to be 1.4. That's actually more constant than the C sub P value, that ratio of the specific heats. So we end up 290 K times 8 to the 0.4 value. Anyone have any opinions on what that value ought to be?
666.25.
Oh boy. Good thing there's a 0.25 on it. We'll keep the 5 digits on that one. So if I want to know the it's not going from 17 to 666, it's going from 290. Change in enthalpy would be that times C sub P. I have to look that one up in a bit. We'll chase the temperatures around here first. I'm thinking also maybe we ought to see what the pressure is. Let me go back, find. Oh boy, different chapter. I'll find the page where we have those formulas. Just out of curiosity, you know, just exactly, did the pressure go up by a factor of 8? Let's see now. Here we go. So these are our isentropic formulas, all the ones with K in them. It should be if I want to find pressure 2, I think we're going to say P2 S is pressure 1 times R to the K. just solving for, and I'm kind of winging it on this one. I think that's right. So it should be 1 atmosphere, whatever that 1 atmosphere is, times 8 to the 1.4.
$18.38.
So we can now write this up here. We got 18.38. That was really only of academic interest. Temperatures are really,
Well, that's it in Kelvin. If you converted it back to Celsius, it'd be 393.3.
yeah, that's, yeah. Wait a minute, say what? Say that again?
That
Oh, yeah.
6.625 was in Kelvin. I converted mine back to Celsius at the end. 393.1 for the charge.
Yeah, I think I'm going to keep them in Kelvin just because we're going to be using the Kelvin so much. So I'm going to keep that to 290. But the pressure went up and the temperature both went up, and it didn't go up by a factor of 8. This went up by a factor of 18. That's the thing about when you compress gas, it heats up, and because it heats up, the pressure rises, and so it's not like water. If you just took like 8 to 1 and you moved it, it would have to move somewhere. It's not going to compress. But the whole thing of air is, with ideal gas law, is give it 1/8 the volume, the pressure goes up more than that if you contain the heat. If the heat rises, it went to 1/8 the space. If nothing else happened, it would go up 8 times in pressure. But the fact that it also heats up when you compress it, there's others. Then that heat also, you had to put the work into compressing it and also the work into making the heat. And anyway, how much work did you do? It's this times the C sub T. We'll get to that one in a sec. Let's chase the temperatures around. So now I want to know what temperature 3 is. So how do I find out temperature 3? The way we do that is the amount of heat that went in. It's the constant pressure or constant volume. The piston's kind of parked there. That's a pretty good approximation of what really goes on. Because 5 or 10 degrees on either side of top dead center, it doesn't move much. So you let off the spark and kaboom, it at a constant volume. Now there's no work going into moving anything. It's all at the same. So all that energy is going to go into changing the temperature. So they gave us Q, and that was 800 kilojoules per kilogram. That's how much combustion we got. We have a C sub V of 0.855 kilojoules per kilogram per degree Kelvin, and T2S we just figured out was 666.25 Kelvin. I want to solve for temperature 3, so how am I going to do that? Temperature 3 is going to be temperature 2S plus Q divided by constant volume specific heat. So I got 666.25 Kelvin plus 800 kilojoules per kilogram. Oops, nope, sorry. 800 kilojoules per kilogram divided by 0.855 kilojoules per kilogram Kelvin. This term here is going to tell us how much more heat was added. This, the first term tells us where it started from. So we're going to end up with what? 800.
1,601.9.
1,000.
601.9.
Is that just this term?
That's the answer.
Yep, I got those two divided, and then I multiplied by that.
Really? Interesting.
Did you multiply or just add? Just add.
800. I would think 800 divided by 85%. It's going to come out more than 800. Oh yeah, 1601. Yeah, I buy it. 60. I was thinking it was 1,000. Never mind. 1600. That makes sense. We'll call it 1602 Kelvin. So now we got 1602 Kelvin, and now I want to know. I'm going to take this back down and re-expand it. And I need to find the new temperature. And how am I going to do that? Same thing as we did before, except there's an inverted formula. So it's T4S equals T3 times 1 over R to the K minus 1.
Can you move up?
Yep. This thing zoomed in too much. So T3 was 1602 Kelvin. 1 over 8 to the 0.4. Now we're talking the power stroke. And for that power stroke to happen, to move that far, it's going to expand as it has high pressure at the beginning, lower pressure at the bottom. We may or may not do the whole pressure thing on this one.
697.28.
All right. I'll call it 0.3 Kelvin. Now we chase the temperatures around. Now we're starting off in our table. Let's see, let me bring that back up so you can see. Started off at 290 Kelvin. Went up to 670 Kelvin just from the compression stroke. Added fuel, went higher pressure, and now the difference in pressure between when we pushed it and when it expanded is what causes, I mean, we have to put work into the system to compress it. We get more work out because we added fuel, now it went up to a higher pressure, it pushes harder. When it comes out, our exhaust is at that temperature. If by some magic we could make the expansion stroke, we could expand that more, it'd get more work. It's still at, we'll do the pressure on it. It's still at a high pressure. That's why you need mufflers. Because if it came out at atmospheric pressure, when you open the valve, there'd be no noise. But if it's at high pressure, you open the valve and it's loud because it's a pressure pulse coming out. Let's see what that pressure is. Let's see, this time it's P4S equals, did we do a P3? We didn't do a P3. Oh, we need a P3 to do that. I'll work that offline. Let's find H2. For the compression, we've got C sub P times T2S minus T1. C sub P. A couple ways we could find it. If the ratio of specific heats is it's 1.4 times our C sub V. I'm using a temperature sort of mid-range in these values. I'm just not looking it up too scientifically here. So the change, actually what I should say here, the change in enthalpy, so H2S minus H1 equals C sub P times temperature 2S minus temperature.
Where'd you get the C sub P again?
In the book. It's a property of air, and that property.
Trying to the back of the list.
Yeah, so I'm looking on page 976. And really what I did was I looked for I got this value. This is what I was using for it's at 1,000 degrees Kelvin, and we're kind of in that range. I use this. I mean, this is changing a little bit with temperature. Ideally, you pick like the midpoint temperature, the average between the two temperatures that you're dealing with. But we need just a constant for this to loop around. So I'm just going to use these two values just because they're kind of mid-range in the values we're using. So these are the two values I'm picking. You know, I could have also just done for air at 300 degrees. These are more commonly you know, those are just that, but that's just at room temperature, and I don't know any engine that operates at room temperature. It wouldn't be much good if it did. So this gives us, and by the way, I to make life easy, I just said, you know, I'm going to say this is my reference value. It's the lowest energy, my input energy. I'm just going to say that's my reference 0. So my H2S is going to be 0 plus whatever this calculation is. So we get 476 times 1.1, 500 and something.
$429.67.
Say again, 5.
429.67.
Oh, 429.67. We'll call it 0.7 kilojoules per kilogram. And H3 minus H2S equals, now this is from 2 to 3, that's a constant volume process, so we're going to have to use a C sub V, constant volume specific heat. And we're looking for teeth, for the value for 3. We have to use this value for H2S now. And 1602.
Did you move it up a little bit?
Oh. Yeah.
For that, I got 800.06.
Bummer. How can that be? That's what it is.
I'm getting 1,742, but I also added H2S and things like that.
Oh, yeah, okay, that's good. So what did you, so for this whole thing, this is the difference. Let's try that again. 16. Okay, I'm buying it actually. What was it? 800.06?
800.06.
And how did we know that? What was the difference? What was the difference between these two temperatures? How did we calculate it? This is just undoing the version we had. They put in what we know. They put in 800 kilojoules worth of energy to raise it up. So H3 is going to be H2S plus 800. This 0.06 is actually a rounding error. Because H2S plus the fuel gave us H3. So should be 1229.7. Because that's all that happened here is Qn was 800. Didn't even need to do that calculation as it turns out. H3 minus H4S. Now it's from here to here, it's an isentropic expansion. We go back to using the C sub P. And T3, what was we decided was 1602 minus 697.3. In ideal gas law, the temperature is affected by pressure, so we don't really need to come up with it's only going to be whatever temperature is because the pressure changed. When it's, we don't really need to know what the pressure is. We can figure it out. But if you add some pressure to something, it changes the temperature. And if you compress something, you don't just go from 8 to 1 with 8 times as much pressure. It's all related to ideal gas law. So what's this one?
I got 1033.2.
All right. And next time we'll go basically the amount of work that went on. Just one last thing. From here to here, that's how much work got done. So it's about 200. We put in 800. What we paid for was 800. So that's that work, and then there was compression work. Yeah. Anyway, that's come up with an efficiency. This one's might be 25% efficient. Okay, that'll do for today.